In this video, we have an example of exponential growth, specifically continuous population growth. Let's say that we have a colony of bacteria and it increases from 12.4 million at 8 a.m. to 37.3 million at 6 p.m. If this growth rate continues, at what time will there be 45 million bacteria? We're going to use the continuous population growth model. So the ending population P equals the initial population, P sub 0, times e to the growth rate K times t. So kt is in the exponent of e. Let's plug in what we know. The ending population is 37.3 million. So that's what we'll plug in here, 37.3 million. And the initial population is 12.4 million, so we'll plug in 12.4 million. And that is times e to the k. We do not know the growth rate, but we do know the time from 8 a.m. to 6 p.m. That's 10 hours. So I'll say times 10. All right, now we have that information. Let's proceed to solve. To solve this, we have to isolate the base and its exponent, this. So let's divide each side by 12.4, and when we do that, we get 3.00806, rounding to 5 decimal places. You should hang on to at least 5 decimal places until the end of the problem. That equals e to the power of 10k. I just wrote, instead of k times 10, I wrote 10 times k there. Now when we have the base and its exponent isolated and we need to solve for the exponent, you can take the logarithm of each side. I'm in the habit of taking the natural log of each side, and that's because when you have a base of e, something drops out very easily, and I'll show you that in just a minute. So now we have the natural log of 3.00806. I'll put that in parentheses. That equals, now we can use properties of logarithms and say, oh, this exponent can get moved out front. So it's 10k times the natural log of e. 10k times the natural log of e. And we can do something else fancy here. The natural log of e just equals 1. So this arrow with 1, and sometimes you see arrow with a 0 in something else, a different problem where it does equal 1 or 0. It's just a notational shortcut. So I could write the whole line again and say that equals 1, or I say, okay, well, natural log of e is just 1. You can plug it into your calculator if you don't believe me, but it is, and so that just equals 1. So now we just have 10k. So you can divide each side by 10. And notice that we are not saying the logarithm of 10. It's just 10. And I am going to just change this color just so you can see it a little bit better. Okay, and when you do this, you can type this into your calculator all at once. Now, most calculators will take this. Make sure you close this parentheses. So natural log of 3.00806, close the parentheses, and then divide by 10. And that gives you 0.11013 equals k. Now we have k. Once we have k, we are going to make our main formula. So let's do this. Let's plug in. We have our ending population equals our initial population, that's 12.4 million, times e to the k, that's 0.11013. We're still working with this problem, so we're going to hang on to all those 5 decimal places. You might round it in another instance, but in this one we'll hang on to all 5 of those. And that's our formula that we're going to work on. And now we're just going to do the exact same thing that we did over here. So we'll plug in the ending amount. The ending amount in this case is 45 million, so 45 equals 12.4 times e to the 0.11013t. Now we'll divide each side by 12.4, and I'm just going to kind of cut to the chase here. After you divide each side by 12.4, you will then get 3.62903 equals e to the power of 0.11013t. And of course, t is what we don't know. We'll take the natural log of each side. I left a little space there so I could fit that natural log in. And then we'll say the natural log of 3.62903 equals, again, we're going to take this exponent, slide it out front, and continue. That is 0.11013 times t times the natural log of e. And just like we did last time, hot dog, natural log of e is just 1. So now we can just divide each side by 0.11013. And remember, when you type this into your calculator, if you type it in all at once, close this parentheses and then divide by 0.11013. And you will get time there. You'll get a time of 11.7. I'll just round there. 11.7 equals t. We're dealing in hours. I'm going to just scoot this down a little bit. We're dealing in hours, so that's 11.7 hours. Let's write that in right there. So after 8 a.m., and you can convert 0.7 into minutes. Just say, I'll just show it right here, 0.7 times 60 equals 42 minutes. So you have 8 a.m. plus 11 hours and 42 minutes. Gives you an end time. Let's change colors for this grand finale answer. Gives you an end time of 7:42 p.m. And at that time, you have that many bacteria, 45 million bacteria. So you can rewind there and see what we did. We put in the information that we had, solved for k, took that k value, plugged it into the k in the formula, and we also put this initial value in the formula, so that gives us our formula, and then we went on to solve for t. All right, I hope that helps.